Particle physics is fun, the same way painting can be fun. Instead of using pigments on a canvas, in physics we put together particles following precise physical principles. Quantum field theory is the mathematical apparatus that tells us how particles come to exist and behave, according to quantum mechanics and Einstein's relativity. Very much like a picture must stay within the canvas, the physical reality must stay within the canvas of quantum field theory. We can use quantum field theory to imagine entirely different universes. For example, take the Higgs boson, the particle discovered at CERN in 2012. Its mass was measured to be approximately 100 times that of a hydrogen atom. It is possible to imagine a physical universe where this mass is 1,000 times bigger. The quantum field theory toolkit would tell us that in that universe, there would be no planets made of heavy atoms, nor stars emitting light, and probably no humans. So with quantum field theory, we can describe how things fit together. But do we really understand why our universe is the way it is? Every child can describe how the hands on a clock take an hour to go around. To understand why they take an hour and not 20 or 70 minutes, the child would need to look inside the clock and observe the tiny wheels and springs. This explanation in terms of smaller things is called reductionism, because it implies that the physics of large things can be reduced to the physics of smaller things. In some cases, reductionism is a total paradigm changer. For instance, electrons and atoms do not collapse into the nucleus. Why? Because in the microscopic reality governed by quantum mechanics and the uncertainty principle, we cannot know precisely where particles are, and therefore it doesn't make sense to think that the electron can fall exactly into the nucleus. With reductionism and quantum field theory, we understand almost everything. But there is one thing we struggle to explain: the mass of the Higgs boson, which is much, much, much smaller than expected. Ordinary massive particles other than the Higgs boson have features that oscillate in all three directions: left-right, up-down, and forward-backward. According to Einstein, instead, particles with no mass, like light, cannot stay at rest. They must travel at the speed of light, exactly like light. At this speed, ordinary particles can only oscillate in the two directions perpendicular to the direction of motion, corresponding to the two different polarizations of light. So for ordinary particles, there is a discontinuity between having a mass or not having a mass. In other words, having a mass makes a massive difference. But the Higgs boson is much simpler. Mass or not, slow or fast, the Higgs boson doesn't care. And this implies we have no explanation of why its mass is so small. What is wrong then? Reductionism, quantum field theory, or the way we are imagining our own universe? Imagining harder, physicists have found alternative universes with reductionist explanations for the Higgs mass. In supersymmetric universes, the Higgs is tied together with ordinary particles, thus explaining why it is light. In other imaginary universes, the Higgs is a composite of smaller ordinary particles, again explaining why it is light. One thing all these alternative universes have in common is that they predict the existence of new yet unobserved ordinary particles. And we can search for them in our laboratories. But what if we don't find these particles? Well, this would challenge our scientific perspective on reductionism, or the foundations of quantum field theory. Or perhaps it would tell us that the Higgs boson is light simply because, if it were heavy, there would be no stars emitting light, no humans, and nobody to ask himself, why is the Higgs boson so light?